In this video, I'm going to discuss reasons for why you might carry out HLM to analyze repeated measures data as opposed to using repeated measures ANOVA. So to cover this illustration, I have a data set already pulled up, and this illustration actually comes in part from Heck et al.'s 2014 text, Multi-Level and Longitudinal Modeling with IBM SPSS. There are two data sets that are utilized in this example. One is a data set presented in horizontal format, where we have each row representing a particular student, and then we have three columns representing students' test scores at time 1, time 2, and time 3. So I also have another data set that's open, which is in vertical format, and in this format we have the same data, actually with some additional variables in here, where we have test scores, and essentially test scores are nested within students. So this is student 1, that person's test score is student 2, with test scores at times 1, 2, and 3, and so forth. So basically, this vertical format is presenting test scores that were previously presented horizontally. So let's do a little bit of a discussion of repeated measures ANOVA and what it accomplishes. Basically, the idea behind repeated measures ANOVA is that we can look at variation in means on a variable over time. That tends to be really the focus of the analysis. So for instance, we have test scores for a group of students at time 1, at time 2, and time 3. And so really what we're interested in testing, at least in the one-way repeated measures design, is whether the means for these variables vary significantly over time. And another question that we might ask is, are there any kind of particular trends in terms of the means over time? So we could, determine whether the trend in terms of the means is linear or quadratic or some other trend. So that's another question that we theoretically could ask. If we had a between subjects factor, we could also look at differences in trends for the means between groups. So that's another possibility. So for instance, let's say I had one group of students that were assigned to a experimental group, and the other group of students that was assigned to a control group. And I might be interested in determining whether the pattern of change over time in terms of the group means vary between those two groups. So for this demonstration, I'm mainly going to focus on just the one-way repeated measures ANOVA, where essentially we have one repeated factor, that factor being time. The repeated measurement is test scores or test, which again, in wide format or horizontal format, we have essentially a variable reflecting each repeated measurement. The idea too is when we're running this kind of analysis is that we are assuming that the spacing of our measurements is equidistant. So the time elapsed between test 1 and test 2 would be the same as the time elapsed between test 2 and test 3. So let's run a repeated measures ANOVA and just take a quick look at this data. So I'm going to go to, in SPSS, I'm going to go to Analyze, General Linear Model, go to Repeated Measures. When this box comes up, I'm going to just give the repeated factor a name. I'm going to call it time. Number of levels, I'm going to assign 3 because we have 3 measurements on our test variable. I'm going to click on Add, and down here under Measure Name, I could actually give the repeated measure a name. So I could actually call it something like Test or whatever and click Add. It's not really a requirement, but I'll do it. I'll click on Define, and when this box opens up, I'm going to move my 3 repeated measurements over to the Within Subjects Variables box. Under Options, I'm going to ask for some of the usual things that I typically ask for when I'm running ANOVA, and so I've got descriptives, effect size, power, and so forth. But and then I'm going to click on Plots, and I'm going to ask for I'm going to plot out the means over time. So I'm moving time over to the horizontal axis, clicking Add, and then Continue. So when I do this, when I look at the output after doing this, you'll notice that the repeated measures data, you'll notice that you get various pieces of information. We've got the means for test 1, test 2, test 3. So you can see that at basically time 1 for our test variable is 48.63, time 2 is 53.1, time 3 is 57.09. So you can see that there's some variation in terms of the means. You'll notice that as you kind of scroll a little bit in SPSS, you'll first be presented with essentially multivariate tests, which are one way in which you can evaluate whether there are significant differences among the means over time. And so, oftentimes I'll rely on Wilks Lambda, so you can see right here that this particular test is indicating statistical significance, which this is basically the multivariate version of testing, are there significant differences in these means? And so based on the multivariate test result, it's obvious that there's evidence for that. If I didn't want to describe the multivariate test, a lot of times what folks will do is they'll rely on the univariate test results, and that's what's presented down here in the test of within subjects effects. And you have actually several different test options available. One of the assumptions associated with repeated measures ANOVA is the assumption of sphericity. And, basically, this speaks to the variation, the pattern of variation and covariation among differences between the time points. So without getting too far into the weeds, this is the basic test assumption results that we have right here. And so, what we would say in this case is if sphericity was assumed, our test results, our univariate test result would indicate that we have significant differences between the means. Now, oftentimes though, when we're interpreting our univariate test results, we want to rely on a test of sphericity or at least some indication of whether the sphericity assumption is met. And there are two ways to do this. Descriptively, there's the epsilon value, which is essentially an estimate that is used to gauge deviations from sphericity. So really values closer to 1 with respect to the greenhouse Geiser and when felt, the better. The more likely it is that your repeated measures are meeting that assumption. Also, there's a significance test, and so if this is indicating statistical significance, then that actually would suggest that we have a significant departure from sphericity. The fact of the matter is that as you're looking at both of these results right here, they look like they are speaking to different results. The epsilon values descriptively seem to be suggesting lack of violation of the assumption, whereas the Mauchly's test is actually suggesting a violation of the assumption. The fact of the matter is, though, that this data set was extraordinarily large. We had, in this data set, we had 8,670 cases. So you can see that we had a very minor departure of our deviations from sphericity when you're looking at it descriptively, but the test was so highly powered. So I would probably be inclined to err on the side of assuming that sphericity was met, because we know that tests of assumptions, the power of those tests are impacted by the same things that impact the power of traditional significance tests when we're testing means and so forth. That is the effect size and then also the sample size. And so you can, as we saw, we had a really large sample size. So the fact that our assumption appears to be violated is not a huge surprise. If we had a more clear evidence of a violation, though, we might utilize the greenhouse Geiser and Huynh-Felt tests, which are more conservative tests of the sphericity assumption. And really, in all cases, right here, we find that the sphericity assumed test and the greenhouse Geiser and Huynh-Felt tests are all statistically significant. So really, there's good evidence of variation or differences between the means. You also see in our output, we've got tests of within subjects contrast. So in other words, what we can do is we can test whether the means are exhibiting a linear trend or a quadratic trend. So you have essentially a test of the linear and quadratic components of essentially polynomial contrast. And so what we're looking for is, we determine which trend better fits the data based on the higher order term within the contrast. And so you can see that the linear trend, obviously there's good evidence of a linear trend, but we also find that there's statistically significant quadratic component as well. So based on these results, there's some evidence of potentially a quadratic trend in the data. Now keep in mind, looking at the individual components though, we see that the effect for looking at the partial eta squared, the effect for the linear trend is quite substantial, whereas we have a pretty small effect going for the quadratic trend. And again, what we're probably wrestling with in this particular example is the fact that we have a huge power due to the sample size. When we scroll down, if we want to get a visual of the means, you can see that right here you see that at time 1, this is the plot of the mean at time 1, 2, and 3. And so you can see that it almost looks linear. There's a whisper of a bend right here, and that's probably what that quadratic component was picking up on in our previous test of the within subjects contrast. But for, in terms of the means, it's looking almost, linear. Now, the downside of this kind of approach I want to draw your attention to is that, really we're looking at individual growth trajectories in the aggregate. So we're basically taking means at time 1, 2, and 3 and making comparisons and then looking at trending in terms of those means. But what we lose out on is the fact that the individual participants or the students within this sample, they may actually be exhibit different growth curves, and that can be a point of substantial interest that we can miss out on if we're running a repeated measures ANOVA. And then also, the repeated measures ANOVA is assuming a similar trending for everybody. So in other words, the growth curve is kind of assumed to be similar for all the cases in your data set, and that may or may not be true. So to kind of provide you with a little bit of an example, what I've got right here is the test scores in the horizontal demonstration, and what I could do is kind of go to the vertical version. So what I've done is I've restructured, or actually this is what the author of the textbook that I was using, that author had restructured the data, and so you had the individual identifiers for each student and basically each student was measured at time 1, 2, or 3. The index variable is actually recoded into a new time variable with 0 being reflecting time 1, 1 reflecting time 2, and 2 reflecting time 3. So you'll see the same repeat across the individuals within the sample. And so these are the test scores for time 1, 2, and 3 for person 1, 1, 2, and 3 for person 2, 1, 2, and 3 for person 3. So let's take a look at the individual growth curves. So in other words, what we're going to be looking more specifically at is the test scores for each person, and do they exhibit similarities, or are they kind of differing in terms of patterns of growth over time? So what I'm going to do, kind of following along with the presentation in the Heck et al. Text, is I'm going to select the first 17 cases in the data set. So I'm going to move ID over here, and I'm going to say ID is less than 18. So I'm going to select the first 18 cases, click on continue, and so now when I click on OK, you'll notice that in the vertical data set, if I kind of scroll down, the lines at row 52, you can see that the cases 18 onward are selected out from any subsequent analyses at this point. So I'm going to go to Graphs, Legacy Dialogues, and then go down to Scatter Dot Plot. And so click on Simple Scatter, and then I'm going to move the test variable over to the y-axis, and I'm going to move I'm just going to go ahead and use the time variable on the x-axis. I'm also going to try to look at the growth trends per student in this data set. So I'm going to move ID over to the set markers by box. So now when I click on OK, you'll see now I get multicolored dots right here, but this is basically reflecting the first 18 students at time 1, time 2, and at time 3. So when I double click on this, I can actually get lines, essentially fit lines for each person. So if I click on this button right here, it says add fit line at subgroups, then you'll see that SPSS generates fit lines, and it assumes that we have linear trajectories for each person. So I like to remove the labels, and so I'm going to click on that and then click on apply and remove the label. And then when I close this out, you'll see that essentially we've got, again, each person measured at time 1, 2, and 3. And this is the first 17 people in the data set. So you'll see, for instance, that when you're looking, you've got, the person with, this kind of blue line right here is probably, maybe person 9 or whatever. You can see that this is that person's score at time 1, score at time 2, and score at time 3. And when you fit the line to this, it looks like this. You'll see that this turquoise line right here, which looks to be probably person number 7, there's that person's time 1, their time 2 is probably right around here, and then time 3 is right around here. And you can see the line actually comes a little bit closer to fitting that person's growth trajectory than this one up here. You'll see the red line, you've got time 1, time 2, and time 3. So, the red line, the linear trajectory, seems to really do a nice job of fitting that person's growth trajectory. That's going to be probably person number 6. So you can see also that when you're looking at this, that we could look at time 1, the scores for each person, as basically representing their intercepts. If you think about it, the intercept within a standard regression model is a predicted value on y when x is equal to 0. So by recoding that index variable into a new time variable with a value of 0 as a starting point, this would be each person's intercept for their growth trajectories. And so you can see that there's, which you would expect, there's going to be substantial variation at time 1. And then you also, obviously, there's variation at time 2 and at time 3. So there's the time 2 and then time 3 for each of these individuals. You also have the fact that the slopes look like they're varying as well. So, like this slope for, this person right here, this is their regression line. It's almost horizontal, whereas you can see that other slopes appear to be exhibiting are more prominently laid out, so more positive relationships. So you can see then that the slopes for each of these individual growth trajectories appears possibly to vary as well. So if we were to use the repeated measures ANOVA, we're making the assumption that the growth trajectories are going to be similar in large part, and if they're dissimilar, as this case might be, then we can't really capture that looking at mean changes over time. We also have, let's try a different growth trajectory. Let's double click on our box here, and I'm going to just kind of click on this little line and try to bring up the previous trends. And I'm going to ask for a quadratic trend. So now when I hit apply, and I'm going to remove the label from the line again, you'll see that in this case, you can see that the lines actually do a better job of reflecting the growth trends. So you can see that, again, the red line right here, it looks pretty linear. But you can see a lot of these trends, look like there's a bend in the line. And the most pronounced one is actually going to be, this line right here where you can see in black, which looks like it's person number 17. So in this case, what that tells me then is that, maybe a quadratic trend would actually fit the individual growth curves better than a linear trend. And so, if I just look at the means on the repeated measures ANOVA, they almost look like they're demonstrating a linear trend. But when you look at the trends for each of the individual growth curves, it looks like there's really a fair amount of variation. And if we model the data using repeated measures, then we lose out on that piece of information. Now, the next issue then, when it comes to the repeated measures ANOVA is, when we are, when we're using the repeated measures ANOVA, then we can't really do a very good job of modeling predictors of the variation in those slopes. We can't really do that. And so, and that may be a substantial point of interest among researchers. Like we might be asking, well, why does this person exhibit, less of quadratic trend than this person right here? And why does this person exhibit a little bit more of a linear trend? So those might be substantial points of interest. And so what we can do is we can model, essentially model predictors of individual growth parameters, basically the individual's intercepts as well as the change over time. So that's where HLM can really come into play and be very helpful, is that we can both model the individual growth trajectories and look at potential between person predictors of variation in those growth curves. So the other thing to kind of note too is that, well, actually we'll stop there, and we'll continue on in the next video.